That's good. Okay, thank you very much, Andrew. I asked him not to embarrass me too much, so that was kind. Well, it's a fantastic honor to be here and to be invited to speak at POPL and talk to you all. I hope to convince you that this is an interesting area, though largely you're already convinced, I think. But still, the question is scientific interest. Let's see how that goes. So I thought to talk about this rather than older work, and this is work I did at Google with Martina Batti during last year, and obviously it concerns differentiable programming languages or differential programming languages. The question is, what are they? So roughly speaking, they're just languages. Oops, that's a mistake. Yeah, I'll take the call. Yeah, that's my wife wishing me well. Yeah. Oh no. Can you kill that? Thanks. I can't do that. Yeah. So they're programming languages where you can differentiate as many programs as possible, roughly speaking. Generally speaking, these programs are functions from powers of the reals to powers of the reals. Why would you want to do that? Because you want to find gradients. Why you want to find gradients? Because you want to optimize something by some kind of gradient descent. Why is it interesting for me particularly to do it? It's just very beautiful. On the one hand, we've got the semantics of programming languages, all the kind of maths we've worked on there over the years. On the other hand, we've got good old calculus and real analysis, and the two are fitting together somehow. And as you'll see, they fit together really beautifully. I was quite surprised. I still feel surprised by that. So that's why I like it. As I've already essentially said, it's in the air, because I noticed that there was at least 4 other talks at POPL in this general area, of which 2 were keynotes at workshops. So for me, I got kind of awoken to the connection between differentiable programming languages and deep learning by the blogs of Christopher Olah, which I recommend you to read. They're very nice. But as you will also see, differentiable programming languages per se go back a long way. Essentially, you can trace them back as far as you like, but I'll show you a reference in the 60s, for example. So let's get started. What I'd like to do, so I'm going to show you some current examples of differentiable programming languages, but I want to place it in a wider context, which is languages for learning. I think there might be a more general area of languages for learning. So I'm going to talk about differentiable programming languages and probabilistic programming languages, just for the first couple of slides. Okay, so probabilistic programming languages in some sense are more established. We had that PPS workshop here a few days ago. There's some higher order probabilistic programming languages. I like to count. Wikipedia listed 35 of them altogether. I don't know, make of that what you want. So in deep learning, I'd like to divide the kinds of programming languages or packages or frameworks that there are into 3 camps. But these 3 camps are sociological, not scientific. So there's the things that come out from the deep learning community. There's things that come out from the automatic differentiation community, which is a very old one. Everything's kind of merging, and then there's foundational studies. And I'm sure there's more than I have here, but I don't think there's an order of magnitude more. So for example, we have these various commercial systems. Obviously, I'm going to know TensorFlow best. So what TensorFlow does is you write some Python program, and eventually you get a graph out of it. And this is a graph of operations. Now these operations map, as you may expect, tensors to tensors, and you're going to calculate something with this. It turns out you want to do more things than just have straightforward or directed graphs. You might want to have loops or function calls or conditionals or maps, all kinds of things you might want, and some of those are already in there. So if you just, as it were, narrow your focus and just look at the graphs, it's already kind of a mini programming language, but not with proper syntax or anything. On the other hand, there's automatic differentiation. An example there is Autograd. These things typically work as Python packages. You sort of import grad function, and you use grad in Python. And NumPy is numerical package for handling tensors. And there's many variations of that. TensorFlow eager mode, gluon, PyTorch, also diffsharp for F#. There's probably more. I know there's a Haskell package, but I don't know what it does. Vlad, on the other hand, is interesting. It seems to be the only standalone language just specifically only for differentiable programming. Vlad stands for functional with a V language for automatic differentiation. So as you'll see, there's two kinds of differentiation you can do, forward and backward. I'll tell you about it in more detail. Gradients are backward, so we want backwards. So Vlad has both in some sense. The other guys are backwards. The foundational studies, there's a differential lambda calculus of which I'll say more. It has forwards only. The perturbative lambda calculus is, from this general point of view, a variation. And then there's a language for differentiable functions, EDLAT and Giannantoni, which is the work closest to what I'm going to tell you about here. So it's like more, it's kind of strictly incomparable. There's many dimensions. So I'll talk about it more, but let me just say briefly that that's only for forward differentiation, and you don't have first-class differentiation, so you can't differentiate things which are differentials inside them. But whether or not that's essential to their methodology, I don't know. It may well not be. Oops, I don't want to talk about that. So with these special languages, you have a nice language surrounding some kind of functional language, and you put special things that you need for the applications you have in mind. So for example, with the probabilistic programming languages, you want a bunch of distributions, you want to make probabilistic choice, you want to do conditioning. With differentiable programming, you want a gradient operation and you want tensors. Maybe I'll spend a second to say what tensors are. So simple tensors are vectors, they're of rank 1, matrices of rank 2, and so on. Once you know the rank, you have to say the dimension. So you say the number of rows and columns for a tensor of rank 2, i.e. a matrix. So in general, if you've got rank k, the shape is given by a sequence of numbers d0 to k minus 1. And this d0, that doesn't work. d0 in square brackets just means 0 up to d0 minus 1. Okay, so it's just, these are the coordinates. And, you've got this matrix at ij, then it gives you the value. Okay, they have their own execution models. The probabilistic programming, you sample from the distribution. Execute in differentiable programming, you could do inference. Once you've got your net, you can learn it. Or you can use it to recognize images or whatever I meant to say. And learning, you have to optimize. There's many parameters. The whole thing is to be able to optimize your parameters. So, but what I want to say next is that these two things are actually not as disjoint as they might seem. Each bleeds into the other. So for example, the Hamiltonian Monte Carlo in probabilistic programming, you go along a gradient. So you have to do gradients, and they do and the language Stan does reverse differentiation. Coming in the other direction, the optimization can be stochastic gradient descent, so some stochasticity, or their neurons, which we'll talk about, can be stochastic. There's many ways in which each bleeds into the other. So maybe we should look for a language which somehow supersedes them both. Or maybe there's other kinds of learning which we should have in our languages. So I think it's wide open. I've no real idea. I just want to point out the possibility to you. Okay, so here's the talk synopsis, for which I've got 45 minutes, I expect. So that's the end of intro part 1. We'll review neural nets. So that's perhaps to let you know a bit about neural nets. But the main reason is by looking at a bunch of examples of neural nets, we'll see the kind of programming language issues which are coming out, just looking at them. That'll lead us to an intro part 2. We're going to have to talk about differentiation, and that'll just be some heavy calculus. But again, apart from any mathematical ins and outs, as a programming language point of view, suppose I've got a function from A to B. What's the type of its differentiation anyway? Is there a general type for such a thing? We want to do a functional language way of doing things. Derivative, that's what I wanted. So once we've got that, that'll be enough motivation for a mini language, and then we can start going on the semantics a bit. But it turns out that there's two problems, which is how the heck do you differentiate control flow things? How do you differentiate conditionals? How do you differentiate loops? Everyone knows how to do these things. Everyone does these things. But why is what they do justified? And the answer is it isn't justified. We need some hypotheses. Then once we've got a nice semantic framework set up, which is basically just a little bit of classical analysis, we'll do the language semantics, and I'll try and talk through a little bit of the source code transformation. So the idea is if you have a program and it's got some derivatives in it, you want to do source code transformation to eliminate all the derivatives. Okay, and this is non-trivial because this language will have arbitrary recursive functions, for example. But then there's a kind of impoverishment about this language that essentially, modulo some parentheses, the types are all powers of the reals. So we don't have sum types, we don't have lists, nothing. So what can we do to get beyond that? So I hope to find some time to talk about that too. Okay, neural networks, a very brief introduction. So they're just a directed acyclic graphs built from simple functions, like I'll come across some of the simple functions next slide, but there's other ones too. But the point about these simple functions is they're parameterized, and you get millions of parameters, and you have to optimize in some giant space. So here's a simple primitive. The neuron, you have a bunch of reals going in, a single reel going out. You take a linear combination of the x's, and you apply a nonlinear function f called the activation function. It couldn't be simpler. But the problem usually comes with what's your choice of activation function. People like this ReLU function now. It's a 0 up to 0, and then it goes along the diagonal. And the nasty thing about that is that it isn't differentiable at 0, but it works very well. So what do we do? So Lakatos had this nice idea in philosophy of mathematics called monsters. Mathematics proceeds by its attitude to monsters. You can either bar them or accommodate them. So I'm going to bar them. I'm going to not allow this one, but I'm almost going to allow it. I'm going to get the partial function, which is identical to that function except at 0, where it's undefined. That function is differentiable everywhere. In fact, it's smooth. It can differentiate it as many times as you like. It's 0, then it's 1, then it's 0, 0, 0, 0. So that's not too bad. Intuitively, if we can prove that some program works, like terminates with that weaker thing, then the whole thing will terminate anyway. So results given this way should, though I haven't proved any theorems, imply that the normal way of doing things works in that case. The trouble is there's other cases in which it works, and that won't cover them. So what can we do? One way is we can also, there's also monster avoidance. So monster avoidance says, I don't like that function, I'll do another function which is very close to it, but is smooth. So people came across this swish function quite recently, and they claim in their paper that in fact is better than ReLU in a bunch of situations. So that's good news. Another thing you can do is you can say, well, look, actually, ReLU is differentiable. Okay, what's its derivative at 0? Well, it could be 0 or it could be 1. Well, it's kind of swinging. So why do we make it the interval 0, 0, 1? And this kind of generalized derivative is called the Clark derivative, and it's a known piece of mathematics, and that's what Edelat uses in his paper. So there's a bunch of things you can do. But what I wanted to do was just the simplest thing, the simplest mathematics that's going to produce some results, just to get some kind of start. Okay, so that's what I do there. So everyone knows this, supervised learning. You've got a training data set, you pick a pair, you run the neural net on X, you compare the output, that's an error, you adjust the parameters, you go down the hill to change the thing. And this is just like, this thing gets more and more complicated. You can make the choices to stochastic, you can, so let me just say a little bit. So this is what you do. So there's the graph, you're going down it, and if your parameter vector was X, the new one X prime is X minus some number called the learning rate times the gradient, okay? So that's all true, but why is it interesting from a programming point of view? Because this R here is not a parameter of the neural net. It's a parameter of the learning process. These are called hyperparameters. We might like to learn the best choice of hyperparameter. So that means the whole program which does gradient descent should be a program that we can differentiate. Okay, there are many reasons why you want to have iterated differentiation, but that's one of them. Okay, here's a 2D convolution network, idealized one, thanks to Ola. And so what's happening, if you see that little A thing there on the left, it's connected to 4 purple things below. So that, if you think of each of these 4 purple things as being real numbers, or having real numbers, and the A thing as another bunch of 4 numbers, then you just take, as it were, the dot product, and that's the output. So it's a linear thing, and you do it all over. So 2 points. One is you want the same A thing everywhere. You want the values of its parameters to be the same. They have to be so-called tied together. So that's a reason to do functional programming, because this A will be a function, and it'll be called with the same parameters everywhere. That's one thing. Another thing is, I'm sure you can imagine in your heads a kind of one-dimensional convolution. Okay? So this thing here, if you look on the left-hand corner, south-north, you can see a one-dimensional convolution. And you can keep on seeing more of them as you go from west to east. So this is a one-dimensional convolution of one-dimensional convolutions. And these convolutions are, in some kind of mapping is going on. So you'd like to do all that in your programming language. You'd like to have nice facilities for working with such things. Okay. Here's another thing. This is the Inception, very successful image recognition architecture. This is, on the left-hand side, that's the general schema for it. And there's a block called, what is it called? The stem, I think. The first one up, second one on the left. And what that actually is the thing on the right, the whole column on the right. So each of these blocks on the left expands into a big column. Each of these things, of more blocks, each of these blocks expands into something else. These things are really big, and they're very deep. So we have to do programming. We have to kind of be modular. There's no way, otherwise it's just not possible. So we need some modularity. Another example, recurrent neural networks. So whereas this is these things were for taking in visual data, these things are typically for taking in auditory or linguistic data, which are coming in from the bottom, and they kind of whiz round. If you know the length of the data, you can unfold it like that. If you don't know the length, you can think of a list of things coming in, and then that's round there is a kind of a while loop. Okay, or if it's an unknown length altogether, then it's some kind of data flow, but nobody goes there as far as I know. Here's a sort of example architecture of that kind, a so-called mixture of experts, in which you come in and then there's some kind of gating thing that chooses an expert to work and you go on. Okay, here's another RNN, a recursive neural net, but it's got an external memory bank that it writes to and reads from. So that's going to tell us that our programming languages ought to have differentiable effects also. Here, differentiable memory, and actually TensorFlow has exceptions. No, errors, I should say. They can't be caught. And they should be differentiable too. And you should be able to catch them anyway. Okay, so there's lots of programming things that come out there. Good, so now we can do the second introduction. So what we're going to do, we're going to study a small functional programming language with products of reals of data types. I'm not going to have any tensor data types. That's a whole orthogonal bag, how to do that. And I haven't thought about it. And that in itself has got a giant history, which Andrew loves. Going back to APL. And again, Wikipedia gives me 21 other array languages. There's a bit of work in functional programming by these people, and there's a Haskell package. I think there's more to do there. Anyway, I want reverse differentiation as language primitive, and I want some control structures and more later. Then give it semantics, do the source code transformations. We also have an operational semantics, but that's not for today. Okay. Previous work, so what about this work, Erhardt and Renier's differentiable lambda calculus? When I came to Google at first, I thought, okay, that's what I'm going to work with. It's really nice. It's a super notion of vector space. The category of these vector spaces is Cartesian closed. What else could you want? But sadly, they don't account for partial functions. So you don't have higher order partiality in them. On the other hand, I have absolutely no idea how to do higher order partiality. So there is a non-higher order notion which actually fits, and the math we use is an example of that, called differential restriction category. Okay, the other strand of work is automatic differentiation. So there, what it does is, given a program, it produces a program to calculate its derivative. It's got a huge literature, a large community. It's very concerned with efficiency, as they ought to be, of course. But despite some searching on my part, I really couldn't find out very much on semantics, on the kinds of stuff, or type theory, or any of the kinds of stuff we like to be able to do. So that's one reason why it's a big opportunity. I think we can hopefully get together with these folks. So there's some references, just put the Wenger there, because that's from 1964. That was forward differentiation. The next one is just a big book, to show you that people write big books on the subject. And if you want to read something, I recommend you start with this survey, Automatic Differentiation and Machine Learning. There's lots of people. Okay, so now, as I said, we want to look at differentiation. So we have to, as it were, gird our loins, or whatever metaphor you prefer. So we all know about differentiation, dEx by dx, and that's a derivative, and we take its value at a. And then we need the chain rule, because what we're going to do is, if we compose two functions, we want to know the derivative of its composition. So we need a chain rule to work it out in terms of components. So the well-known chain rule is derivative of f naught g is derivative of f times derivative of g. So you have to evaluate the derivative of f at g of x. Okay, that's what everyone knows. To make that a little bit functional, we can define this derivative function, which takes a function and gives its derivative. And we can define it as df equals dfx by dx. And I like this example because it shows you how horrible traditional mathematical notation is. What on earth does that mean? dfx by dx is great because the bottom x is both free and binding. And that, with a free variable of x, is not a function. I'd have to do a lambda. Okay, so it's not quite where we want to get to, really. So anyway, so the chain rule in terms of these functional things is a bit better. d of f naught g is d of f at g, d of f naught g, times d of g. So that's a bit better. It's still not that great because there's a multiplication in there. It'd be great if we could get rid of that multiplication, which we will. Okay, now things get worse because Bob's, have you been there? Yeah, anyway, so especially with several variables, we have partial derivatives, and the chain rule now depends. So you want to have the derivative of this compound expression f of g and h with respect to x, but you can get to x in two different ways. One's via the g and one's via the h. So you have to multiply for each of the two different paths and add it up. Okay. And that's made a bit nicer mathematically by introducing the notion of a gradient, which just packages the three partial derivatives together in a vector. Okay, so there it is there, and that's got the same amusing free variable thing in it, but anyway, there it is. Okay. Now, that's the derivative with respect to x. We can repeat the same formula 3 times for the derivatives with respect to the other free variables x, y, and z, and we get this thing coming out, and if you stare at it, you'll see a matrix in there, which is actually that one on the right. Okay. And so that thing is that matrix times the gradient. I've written that down in the bottom line. So that's a matrix, a multiplication. Well, I guess it's a vector in a matrix. The action of this is called the Jacobian. So you take the Jacobian and you take its transpose and you act on the gradient. And that formula says everything up there. Okay. What should I say about that? There's a reason why we didn't define the Jacobian as the adjoint in the first place, which is because it goes the wrong way around, but if we had. But we'll see that, I hope. Anyway, so for Jacobians, what are Jacobians? Well, they're functions which, given an m tuple of reals, give you back a vector. Okay? And it's going to be an n by m vector, so that's going to go forwards. It's going to take n vectors to m vectors. So that's going in the right direction. That's why we want it that way. The gradient, remember, intuitively is going backwards anyway, so we're going to take a transpose. So there's the chain rule for Jacobians. That looks more or less like the chain rule for derivatives, and we've got a dot in there as before, but this time the dot is matrix multiplication. Okay, so that's quite good. But now, the trick is not to be satisfied with this. We notice that, in fact, for every function from r to m to r to the n, we can define a new function, which is going to be called the derivative of f, or the differential of f, and that goes from r to the m squared to r to the n. And what does it do? Well, the first argument, it takes a Jacobian. That's a matrix, so I can apply it to an Emery vector, and I'll get an Emery vector. Okay? It's not hard, and it's a linear, so this function is actually a linear in its second argument, but not in its first argument, because it's matrix multiplication. And in the work by Erhard and so on, they're in a linear logic setting, and they can make these distinctions in their type theory, but I'm not doing that here. Okay, then the chain rule for differentials, at last, we can make the dot into a circle. So there's the chain rule for differentials. At x, the differential of g naught is the differential of g one step later, composed with the differential of f at x. That's really, really nice. Now, with that idea, we're purely functional and doing differentiation as long as we have this derivative, okay? But that's going forwards. We want to go backwards. So what does it mean to go backwards? So if the forwards one goes from r to the m to r to the n, the backward ones had better go from r to the n to the r to the m. You can imagine that your functions are coming along and you're pulling answers and getting previous questions. So where am I? Oh, yes, here. So we define the reverse derivative as we did in the case of the chain rule. We take the transpose of the Jacobian and apply that to the appropriate length vector, which will now be length n rather than length m, and we'll get back an Emery vector. Or from linear algebra, that's the adjoint of the ordinary Jacobian. And the chain rule is the same as the chain rule before, but backwards. Okay, so this is the thing to have in mind. So the differential of g naught f is you first of all do the derivative of the last thing, which is g, at the place you get to from the first thing. And then you do the derivative of the first thing at the place you started from. It's all very backwards. And after a while, this feels natural, and then you lose it again. But once you've got these things, these are generalization of the Jacobian, of the derivative, and you can get derivative. So if f is from r to the m, if f is r to the m to r, then it's reverse differential, apart from the first argument, is from r to the m, as a typo, and then the gradient you can get from that by applying it to 1. This is just a special case of if I've got a linear function, I can recover the matrix that corresponds to it by applying linear function to unit vectors. That's just an example of that. So that's a whole long story. What's the takeaway after all of this? Takeaway is that we have a functional notion of derivative. We have a functional notion of reverse derivative. If f is from r to the m to n, the derivative is from m squared to n, and the reverse one is from m cross n to m. In particular, we get the gradient's a particular case. And I should just say, in some sense, this derivation of the derivative was kind of clunky. We worked our way from derivatives through partial derivatives. We put it all together in a matrix. We got a linear function. But you can do it directly in the sense that the derivative is the best linear approximation to f in a certain sense of approximation. This is a vector-valued version of the usual definition of differentiation of functions of one variable. So I just want to say that that exists. One does not need to be that clunky. Okay. So now we're happy. Now we can do a language. Okay. The language is exactly what you would think. Types are very simple. We've got sums, operations we're going to have. The second thing is the most important thing. This is the syntax for the reverse derivative. Okay. So the function we're defining the reverse derivative of is this lambda xtn in there. We're taking its value at m. I'm allowing myself subscripts. And the thing we're pulling back is this L. Got local definitions, products, conditionals, and recursive definitions. Okay, and it's got a standard enough typing. For example, there's the rules for operations that you go from T to U. There's the rule for derivatives. It just puts into type theory what we've just been saying several times. I think I won't go through it. Okay, so now we can say, okay, how are we going to do semantics for this? So let's get into some actual problems. So what happens with conditionals? I wish I had asked you before, but you should suppose H is if B then F else G. How would you differentiate that? So the rule is that derivative of H is you keep the conditional alone. Anyway, you can't differentiate it because it's Boolean valued. And you put in the two derivatives at each of the branches. That's not unreasonable because if H of X happens to be, if B of X happens to be true, then H of X is equal to D of F of X. H of X is equal to F of X at that X. So why not differentiate there? But the answer to the question is, why should you? It's just because it's true at one value isn't enough. And here's a little example, which I think I've got a feeling time pressing. There's simple examples to show that these things just don't work. This example which gets it wrong, and this is an example you can define ReLU, which isn't differentiable anyway, so you shouldn't be able to define it. So what's the answer? So the answer, as I said before, is we switch to partial things. Okay, so I'm going to make my conditionals partial, and I'm going to make my functions partial, allow them to be partial. Anyhow, I'm forced into that. Even if I don't start off with it, by the time I do recursion or loops, they're going to be partial in any case, often. So let's talk about, say, what does it mean for a partial function from reals to reals to be differentiable? Well, the answer is it just means what it always meant, To be differentiable, you have to be differentiable at every point. But here, since it's partial, you mean at every point where you're defined. Okay? But to know what it is to be differentiable at a point, you must be defining a little area around it, a little open around it, or here a little interval. So we ask that the domain itself of the function is open, and then to be differentiable means that every point to be differentiable in the usual sense. The analog for discrete values, things like the conditionals, is that the places where the condition evaluates to true and the places where it evaluates to false not only should be disjoint, of course, but they should be separately open. Okay? So the proposition is that as long as those two things are true, then the usual rule is correct. Okay? And this actually is in the literature, some version of the automatic differentiation literature. Here's a quick proof. So suppose b of x is true. Well, then actually it's also true in a little open area around that. So in that whole open area, h and f are the same, so therefore they have the same derivatives. So now it's easy. That's good. Let's happily carry on to while loops. What's the rule there? Well, suppose h is while b do f. Suppose it goes around the loop n times, then h of that particular x is f of nth x. So therefore, derivative of h you get by taking the derivative of f to the n using the chain rule. That's false, but it's true assuming all these continuities happen. And it's a similar argument that it's an open set. So a little bit more complicated, but it's basically that's what's going on. Anyway, how would you compute the derivative? Well, what it looks like you have to do is you have to go around the loop to find out when you're going to get to stop. So you should remember all the intermediate values. Once you've got that, you can do the chain rule backwards using the intermediate values. And you can either keep that, if it's like an interpreter or a compiler, you can keep that in some separate data structure, or you can do a program transformation in which you take the loop and you translate it into two loops. The first loop goes around the first loop, accumulating the values and noting when it stops. And the second loop does a countdown from the value where it stops, doing the derivatives as you go along. Anyhow, that is not efficient in the least. But there's methods of doing it. If you translate to a normal form and then apply the chain rule, you get what some people already called automatic differentiation. And that turns out to be equivalent to the backprop method, which was used for neural nets. And so like anything, everything's been discovered a million times in various forms. And there's a nice paper on that there by Grievank. Okay. But that's just kind of playing around in a way. These are just unary functions. We want the same things to be true for functions of m arguments to n arguments. Okay. And I've just said to you the chain rule, but the chain rule is actually false in general. You have to have some axioms. So to get the structure, we have to have functions of the right kind. Okay. And it turns out, well, let's see what we could do. So for a function from R to M to R to N, for it to be differentiable, it's just the same as we had before for functions of one argument. Except instead of the open sets essentially being intervals, now they're balls, or circles, or balls, or whatever. But we also need, but then we can construct the Jacobian and so on, but the chain rule is false in general. We need an extra, intuitively what's wrong with just having the Jacobian is the Jacobian says if I've got a function of several arguments, then I can differentiating it going along one of the axes, either any of the axes, but you can approach it in other directions too, and you really want to have differentials along these paths, and the chain rule essentially forces you to do that. So we need that these derivatives exist in along all paths, and there's a nice theorem that if they exist just along the coordinate directions and they're continuous there, then they exist along all paths. So what people normally do is they just assume not only are you differentiable, but you're continuously differentiable. Okay, so the derivative exists, and as a function, the derivative is continuous. So that's just spelt out there in terms of gradients and Jacobians and so forth, but let's just leave it on. Now we've got partial functions, and we're going to order them. Now we're just going to do bog standard domain theory 0, 0, 0. So partial functions, we're just going to order them by graph inclusion. Another way to write that is f is less than g for every x. If x is defined, then g is defined and they're equal. That's a kind of one-way cleaning equality sign. That makes the set of such partial functions a CPPO. It's got least element bottom and it's got arbitrary soups, so arbitrary countable soups. And it makes conditional construction continuous. So that's really nice. So suppose f and g are actually continuously differentiable, then the reverse derivative, actually also the forward derivative, but I just care about the reverse derivative, acts monotonically on it. So that's a kind of a nice thing. These things are now not quite obvious, but they're obviously the nice things that you want to have happen. Suppose you've got an increasing sequence of continuously differentiable functions, then the soup is also continuously differentiable, and taking the derivative commutes, either forward or reverse, commutes with the soup. You couldn't ask for anything nicer. So for conditionals, we have the statement, which is a generalization of the previous proposition, that if B is continuous, the FG are continuously differentiable, so is their conditional, and the reverse derivative commutes with the conditional. Okay. While loops, we do the usual iteration, and this is a theorem that I'm not going to get into too much detail. It's just the mathematical justification of the intuitive thing that we had before. But this I want to spend a little bit of time in, if I've got any time left. I don't know how much time I've got left. How much time do I have left? I have time. Okay, good. I have time. So there's the while loop. We can define recursively w of x equals if b of x and w of f of x else x. Equivalently, w equals if b, then w naught alpha is identity. Suppose we reverse differentiate that. We know we can push the reverse differentiation inside the conditional. So we get this last line there, second last line. So that suggests making a recursive function, making dx, the reverse derivative of x of w at y into a recursive function, g of xy, which we're going to define. And it suggests making that definition there, g of xy. I write functions of two arguments with the first argument as a subscript. So we can make that definition. And the theorem is that the reverse derivative of w is the least function, g, satisfying that equation. Okay? So that's a source code transformation for this particular recursively defined function. And the way that the source code transformation works is you just take the definition of the function and you differentiate it. That's all. Okay. And actually, if you look at that recursive definition and you imagine calling it, then you'll see it keeps going down the loop, building up the intermediate values on the call stack. And so in the call stack, it keeps all the values, and then it can go backwards. So it's kind of cute. Okay, good. So now we can begin to do the semantics. So we know what the reals are, and we know what products are. We've got functions from t to u, but I actually want functions from so the idea is we'll have a function from t to u, but it's really a function from r to m to r to n, where m and n are, roughly speaking, the sizes of t and u. We don't know what it means for a function from t to u to be differentiable or anything else, but we do know what it means for a function from r to m, so we can translate backwards and forwards by this kind of flattening idea. So there's a kind of a flattening function which, given a u, or rather its meaning, gives you r to the size of u. And so we can, given f, by tracing around these flattening functions, we can get a flattened version of f from rt to r to u. And we're going to say that f has property blah if and only if it's flattening. It has property blah. So, but what we have so far is still not enough. Okay, because our functions are going to be differentiable, so that means we can differentiate them, but we want to iterate differentiation. So we want our functions to be differentiable as many times as we like. So this is just called smoothness in literature. So we want our functions to be smooth, and this is, I'm not actually going to go through it because I know that time's pressing. It just says that we can differentiate as many times as we like, and we're still differentiable in the various Jacobian frameworks and so forth. Yeah, and in terms of partial derivatives, it means you can take partial derivatives of all order as long as you like. Okay, that's good. So what we actually want to do, where's it gone to, is we write smooth of tu for collection of all such functions, and it turns out that's also CPO, the soup of a bunch of smooth functions is smooth. And so we're in a good place to do very standard semantics of the language, and in some sense, there's nothing to say about this. It is the completely standard semantics of everything, except for the one non-standard place, which is the reverse differential. But we know we have these reverse. We've spent the whole time talking about them, so we just use them in the semantics. So there's really nothing to say about the semantics. And what I would like to do is to start talking about source code transformation. But I'd like to know how much time I have left also. 10 minutes. Okay, that's cool. Okay. So it turns out some interesting things turn out. So what we would like to do is start systematically going through all the language constructs and write something, for any given language construct, write reverse differential of that language construct and see if we can simplify that. Okay, and if we could simplify everything, we'd be done, right? But we can't. Anyway, but so starting off, initially we can. We take the function x, and it gives you a variable y. Well, if y equals x, that's the identity function. And then the Jacobian is the identity, and the differential is also the identity. So the result is we just give y a... Oh, have I made a mistake there? Oh, yes, in case y is x, you just give a x back out. So one thing I've done there is, first of all, evaluated q and evaluated p. And that's because I would like these transformations also to hold in the case where we have effects. Okay, so this reverse differential is a function, functional which takes two arguments and a function. So it's going to evaluate the functions, the arguments first. I'm just assuming that we're doing the p before the q, because that's the first argument anyway. Okay, so I'm always going to have this kind of double-let thing. The source code transformation of a sum is a sum of the source code transformations. Everything's linear, there's nothing to worry about. So the operation is the first place where maybe something a little interesting happens. So op of m, so we want to go reverse through op of m, so we better go through op first, and then we'll go through m. So we assume that language magically for every operation provides a reverse derivative for it, called op r, I guess. Yeah, op r. So this dot there, yeah, this dot here, it's just a way of doing function application. So it means this applied to that. It's a well-known convention for function application. So the first thing you do there is you take y and drag it back through op in the reverse direction. And having done that, you drag it back through m. So that's pretty good. So we're probably feeling moderately cheerful. So we can do local definitions. Well, conditionals, we actually know how to do conditionals because we spent ages talking about it. So this is just a tactic version of it. I won't go through local definitions, but I'll just give you the idea. You see, let y be m in x of xy. And we want to drag backwards from n, and we want to get out to x. And there's two routes. We can go through n and come back just to x, or we can back at y, but then the m comes in, so we have to go through m. So we take each of these routes and we add them up. So this is just a syntactic witness to the kind of sums that occur in the chain rule. Okay. And this is, remember, we talked about graphs at the beginning, and if we're to get efficient versions of backprop functionally, we need to do graphs functionally. So, and we will be doing that by these lets. The anormal form will be a whole bunch of lets. So this rule will be used many times. Okay. So now here's where the trouble comes in. Well, first of all, let me tell you some intuitive things. Suppose I've got a recursive definition of f. I want to differentiate it. Okay, no problem. We differentiate the body. Oops. What happens if in the body f is differentiated? That's no problem. We need the derivative of f. Okay, well, so we'll get the derivative of f, and we'll differentiate that. Oops. Derivative is derivative. We're in an infinite loop. Okay, so there's essentially no way around that I'm aware of. So we forbid recursive definitions in which the defined function occurs within the scope of a reverse differential. Okay, that's one bad thing that can happen. Another bad thing that can happen is that, so in this case, so you see, I've let f equal m and n, but notice that m only, it's meant to indicate the only relevant free variable of m is y, i.e. that x is not occurring free. Okay, and I don't know how to handle things when Martina and I suffered terribly. We kept thinking we had it, but we didn't. So the trouble is what's happening, if you allow m to have x in it, then there's another path to x in n of x of f, but that path will depend on how f is applied. And I don't know, maybe there is a way around this, but we didn't get around it. So what I'm actually going to do, the coward's way out, I'm going to forbid all global variables. It's not too bad. It's not entirely cowardly, because you can always take a program in which global variables are allowed, and by redefining things, you can rearrange it so there's no global variables. It's quite easy to do that, but it's not the most elegant situation. So that's one thing. So what that thing up there is saying is that derivative of a recursive of n in the context of a recursive function is just a derivative of n in the context of a recursive function. That's true with these restrictions, but it's unhelpful because we might need some derivatives of f in the body there. So here's the derivative of the function application. It's exactly the same as the case for op, okay? Except we know that in advance that we're guaranteed to have a reverse derivative for every op, but why on earth should we have some suitable f prime available? There's no reason why we should have it, okay? So what do? So there's two strategies. One is to mend things at the first case, which is you somehow look ahead and count how many derivatives you want. The other thing you can do is not look ahead, but every time you have one, you accumulate it. So I chose the second one. I mean, I don't think there's any. For some reason, I thought it would be easier. It wasn't very easy. So I just want. So this is roughly this is a very rough picture. I think I'm going to switch forwards pretty fast after this. So the idea is you've got a state, which is the recursive definitions you're accumulating of the various derivatives you need. It satisfies various criteria. And we think of judgments, so of the form delta slash m goes to delta prime slash d. I wanted slash rather than the environment, the v dash, because there's no guarantee, that's not the case that every free function variable in f in m appears defined in. There's a case in which that doesn't happen, but I'm not going to go into it. Anyway, so what you're doing here is you're symbolically differentiating m until you get to d, which is no derivatives left, and you're accumulating these things on the way. And then the theorem is that under some circumstances, this thing always terminates uniquely, and the semantics of the one is the semantics of the other. And I've like 90%, I'm pretty confident of this. I've proved a lot of it. I'm going through all the details, but I've gone through the nasty parts anyhow. Okay, but this is a nasty system. And I've got 4 minutes, which is perfect. Now, let's do, so far we just have powers of reals. How about sums? Well, sums aren't that bad. Let's think about partial functions from, these can just be sets, a plus b to c plus d. It turns out that such a partial function can be divided into components. Because let's take an element of a and apply the function to it. Well, you're either going to end up in c or d. Okay? So let's take all the elements in a where you end up in c. Then we'll get a partial function from a to c. And carrying on, we get 4 components, okay? And it's pretty obvious that any 4 components satisfy some obvious condition to give you such a thing. Now, these components, if a, b, c, and d are powers of reals, are exactly what we care about anyway. So why don't we just say that f is smooth, differentiable, whatever, if and only if each of these components is smooth, differentiable, whatever. What about its derivative of such an f? If here doing the reverse derivative, so we want to go from a plus b cross c plus d to a plus b. Well, such a function, I can expand the left-hand side out by multiplying out over the sums, distributivity. And so essentially that function is from this sum of 4 things to a plus b. So I'm going to, but that's from a sum of 4 things to a sum of 2 things. So I should have a large number of components. But I don't get to all components, that's right. So, for example, if I want a function from a cross c to a, I've got a function from a to c. That was one of the components. So I can take its derivative, and that will give me a function from a cross c to c, its reverse derivative. And these are all the possible ones we can get in that way, and everything else we're just going to make undefined. Okay, we can write that out as a big conditional, but I'm not going to bother with that too much. So that's a general strategy for taking reverse derivatives of functions from sums to sums. So with that, one can, for example, add sum types to the language, and this is the beginning of that. So in left, so imagine going backwards along in left. So we start off from a z in a plus b. Well, if it's in b, that's a bad place to start from, since you're supposed to be doing an in left, so it should be undefined. But if you're in a or in left of a, you just give the if you're in. You give the y that you came from, that's right. And that gives a corresponding differentiation equivalence. So that's very pretty. I'm not showing you the one for cases because there's lots of symbols in it. But it's really quite straightforward. You can do that too. The question is, how many data types of this kind can we get? What we allow ourselves, we allow ourselves binary products. Actually, we can allow ourselves arbitrary products. Actually, no countable ones, I think I want. We can't allow ourselves, so I said the wrong thing, arbitrary sums, countable sums. We can only allow ourselves finite products. So we should allow ourselves sums of products. So I call these differentiable shapely data types. So we have a set of shapes, that's the index of the sum. And for each set, we have a collection of places, and we have r to that power. Okay, there's lots of these things, as everybody knows from Barry's and everyone's work. We have sets, or trivial sums, finite products of special case, lists of reals, or sigma r to the n, tensors of rank k, or this nastier sum, binary trees of reals, or you sum over all binary trees, and the places are the branches. So you get all kinds of things. And what's more, as I said to you, these data types are themselves closed under finite products and arbitrary sums. So in that R there, I can put any other data type of this kind. So I can have binary trees of tensors or binary trees of lists. And all of this stuff is differentiable now. So one's very happy. Now, getting towards conclusion, what's even nicer is that this isn't arbitrary. These are just special cases of manifolds, of differentiable manifolds. So speaking very fast, so think of a circle. That's a manifold. Each little point in the circle is a little arc. And that's equivalent to a little flat piece of the line. So a manifold is a topological space in which you can patch together copies of r to the n, perhaps for varying n. So these things there are exactly like that. Where's it gone to? Yes. The various places are the S's, and each place you've got a whole copy of a power of r. So these are all manifolds. I know I'm going too fast, but just want to give you the general idea. And with this notion of manifold, then notions of differentiable functions and their derivatives turn out to be exactly what we, as it were, ad hocly defined a second ago. So we fit within a very standard piece of mathematics. It's well known in mathematics that you can't always expect of a vector space, but you can very often expect of an isostructure like a manifold of some kind. Manifolds occur a lot in learning theory. There's PyManopt, which I like, which is Python manifold optimization package. There's many other things to say. And so the obvious question is, should differentiable programming languages have a suitable version of manifolds as their data types? And this question I read was first asked by Barry Perlmutter in the NIPS Autodiff workshop a couple of years ago. So that's the end, except for future work. I might spend a second on that. I was just generally wanting to show you, I mean, I've done whatever I've done, but there's lots to do. There's lots of questions. So here's some questions. How about higher order functions? We can either do things internally or externally. We can add higher order functions to language, and then we either can or can't differentiate them. If we can't, we think of them as external to differentiation, otherwise they're internal. So we can have two versions of each question. So what about effects? I think they can actually be done internally, I'm pretty sure. Probability, I have absolutely no idea. It's really nasty how to do that at all, either way around. We could connect, how about, that's been the most trivial amount of domain theory. How about a bit more interesting domain theory? Streams, for example. Recursive data types. How about metric spaces? They're surely important, because you want to have some notion of being closer to things. How about doing them? What else? Well, this is more like, how about getting closer to what people actually do, making weaker assumptions? How about applying this to what people have already done, automatic differentiation, to prove their compilers are correct? For type theory, the shape analysis, dependent types question for these kinds of arrays. I think it's not the same as the general one. And finally, I'd just like to say the same thing I said before, programs with manifolds. So that's the end of my talk. Thank you very much. I hope I've persuaded this is interesting, and I hope you guys feel like working in this area. Thank you.
Okay, we have some time for questions. And after the questions, we'll have the lightning round previewing the talks from today. Yes, go ahead, Avik.
Is there a notion of abstract interpretation in this language? So if I have to ignore the if construct and think about all paths together, maybe it will help me compute a derivative that is faster to compute but more approximate. Do you have these kinds of notions in your?
No, I should say there's a much more general question that you could have asked. Take anything that's interesting in programming language theory. I mean, I'm not trying to be nasty. Is there a version of that which could help here? I mean, it's a really good question. And that's one reason why I think it's an exciting area. The simple answer is no, but there should be. And there should be many other things as well, affecting all kinds of stuff. Thank you.
Thank you.
So you asked the question about, should there be a programming language for programming with manifolds essentially as data types?
Yeah.
Do you think that there's any relevance to like smooth differential geometry, synthetic differential geometry, or like smooth infinitesimal analysis in that?
Yes. I mean, yes. I mean, yeah. I mean, I didn't mention that. I don't know that work well enough, but you could be working in that universe, as your semantics. But the thing is, if we're going to do domain theory, you see, then we can't do Hausdorff manifolds, so it can't be exactly what people have done. And the programming language point of view is, what's a nice type system for working with a large variety of manifolds? If you looked in that Pyman opt, then they just say, here's a library of manifolds, and we can work with them. But is there a nice way of combining manifolds together which gives something smooth? Yeah. I mean, I've not answered your question, of course, but one could debate.
So unfortunately, we don't really program with real numbers.
Correct.
So, I mean, most of this stuff is done with floats or even 8-bit numbers. Fixed.
Yeah, exactly.
So do you have any
Yes,
insights?
thanks again. There's all these points I meant to make, and I forgot them. So, yeah, so that's one reason to work with metric spaces. So you would have a logical relation between the real things you compute with and the real numbers. And maybe that'll work. But the problem is that if I take the approximation and differentiation don't commute. So that's really annoying. The paper by Edlat and so forth didn't work with real numbers, I should say. They work with computable real numbers. So that was a bit helpful. Yeah, so that's a whole other, so thank you. That is indeed a whole other area to look at. But there's all this annoying thing that they don't actually care anyway because they get good results.
When I was in business school, we had to study topology and function analysis because the spaces were so different from normal R spaces that we had to first do compactness for to solve problems in the business school. I don't know what I did today. One of the things was, one of the big lessons that I always emphasized was don't take the normal interval topology on a real for granted. But your entire talk seems to be just take normal intervals.
Yes.
Have you thought about changing the topology looking like other topologies of the R?
Why would I want to?
Because there are business, there's a series of problems, optimization problems.
Oh, in business? Oh, I see.
Yeah,
oh, cool.
Not use that normal topology.
Oh, that's interesting. Yeah. So maybe that's yet another source of interesting data types. Yeah, thanks.
Can the folks who are in the lightning round come up here while... We're not done yet, but I just want people to start queuing up. Yeah. I think we have another question here.
Hi.
Where's the question?
Just ignore them, Gordon.
Oh, yeah.
So when we train a neural network, it usually takes several days. So we really don't want to have any exceptions or errors happen during that time. So do you really think the assumption, allowing partial functions is realistic?
No. But the point is, do you also want the training thing to make false mathematical assumptions? That's what I tried to say. I wanted to go the mathematical route. I wanted to take the simplest mathematics, which will give me some results. Then I know it's not realistic. I said that from the very beginning. But at least I've got somewhere. I've got some source code transformations. And if this thing predicts... I mean, I talked to someone, and they bloody well do evaluate a ReLU at 0. But they're happy with Swish, on the other hand. So I don't make an absolute yes or no to you. I think it's a complex
Thank
issue.
You.
Yeah.
Okay, one last question.
So I got a bit lost at the end, so I apologize if I just missed this. But how does this extend to more exotic systems, like complex numbers, for example, or different fields?
But they seem to use reals, so I didn't think about it.
I mean, yeah, fair enough. But I mean, you know, kind of interesting properties like analytic, whether or not something's analytic and whatnot. Do these types of systems extend well?
I mean, I can only say that in this application area, it seemed to be intrinsically connected with the reals and not with the complex numbers. So I did the mathematics that seemed relevant to that. I mean, I quite appreciate there could be differentiable programming with complex numbers, and that could be of interest and it probably has lots of applications. I just don't know what they are, and they're not these particular applications. Yeah. As far as I know. The real learners do all kinds of stuff. I'm sure there's some paper that uses complex numbers somewhere. Yeah.
Well, this has been truly fascinating, but we have to move on to the next part. Thank you very much, Gordon.